Graph the following function using the techniques of shifting, compressing, stretching, and reflecting. Start with the graph of the basic function. Find the domain and range of the function. We want to do that with g of x equals 4, absolute value of 3 minus x. So what I'm going to start with is rewriting the inside of this absolute value. So we're starting off with this g of x equals 4, and I'm going to rewrite those terms so that it's negative x plus 3. I'm doing this so it matches the format of the transformations that we have memorized. I'm also going to factor out this negative. So if I factor out the negative, I'll have x minus 3. Negative x minus 3 inside that absolute value. So now that I have it in this format, I want to identify the base graph, and the base graph can be identified with those absolute value bars. We know that we are starting with a basic function of y equals absolute value of x. We know that the graph of y equals absolute value of x is a V-shaped graph. It comes to a point right at the origin 0, 0. And then from there, I want to identify these different transformations. We've got this 4, this negative, and this minus 3. These are 3 transformations that we've got to apply to the basic function of the absolute value graph. So let's figure out what those different transformations are. So we have this multiplication by 4. We have a multiplication by a negative 1 and a subtraction of 3. So when I think of the big categories of transformations, we have the category of shifting, and shifting is going to happen when you have adding or subtracting within your equation. So I only have one subtraction, that's minus 3, so that's going to be a shift in the graph. Then the next category of transformations is stretching and compressing. And stretching or compressing happens when you multiply by a number. So it's multiplication by some number. So that multiplication by 4 is going to be either a stretch or a compression. And then our final category of transformations is reflecting, and reflecting is going to happen when you're multiplying by a negative 1. So we've got multiplication by a negative 1, so we have a reflection. So I've identified the big categories of what these transformations are, but there's a lot more details to figure out because there are vertical stretches and compressions, there are horizontal stretches and compressions, so we need to figure out which type this multiplication by 4 is. With reflections, there are 2 different types. You can have a vertical reflection or a horizontal reflection over the x-axis or y-axis. And for shifting, you can shift left, right, up, or down. So we really need to narrow down which type of each one of these we have. So one thing we can pay attention to is whether the transformation is occurring inside or outside of our basic function. So our basic function is that absolute value. So we're going to look on the inside and on the outside of the absolute value bars. So the 4 is outside, the negative is on the inside, and the minus 3 is on the inside. Transformations that are on the inside will be horizontal transformations, and transformations that are on the outside will be vertical transformations. So we know that our stretch or compression will be a vertical one, and our reflection will be horizontal, and our shift will be horizontal. So that narrows down. The reflection is a horizontal reflection, meaning that it reflects over the y-axis. And we don't need any other details about that transformation. Now, with the stretch or compression, we need to figure out which one it is, whether it's a stretch or compression. So with vertical stretches or compressions, we pay attention to the value that we're multiplying by. And if that number is greater than 1, we call it a stretch. And if that number is in between 0 and 1, we call it a compression. So in our example, because the number we're multiplying by is greater than 1, it's a stretch. So we now know that we have a vertical stretch by a multiple of 4. And then with our shift, we have a horizontal shift that's either left or right. And moving to the left would be a plus, and moving to the right would be a minus. So because we have a minus, we know that our shift is going to be to the right 3. So we can now use these transformations to draw the graph of this basic function. So if we start off, I'm going to start off by graphing our basic function y equals absolute value of x. I'll graph that in black. Then I'm going to graph y equals negative absolute value of x. That's going to be, let me choose a color for that. Let's see, I'll graph it in this orangish color. And this is going to show our horizontal reflection. So then I will graph y equals absolute value of negative x minus 3. And this is going to shift our graph to the right 3. And then finally, I'll draw the graph of y equals 4 times the absolute value of negative x minus 3. And this will include all 3 transformations. So the graph of absolute value of x is a V-shaped graph starting at the origin. And so it looks like this. And that first transformation, which is the horizontal reflection, is going to look like we didn't change anything because this function is an even function. It has y-axis symmetry. So when we mirror over the y-axis, it looks exactly like it started. So then I'll shift all of those points to the right 3. And we get this graph in the light blue. And then I want to multiply by a factor of 4, stretch out the graph by a factor of 4. So instead of this going up to 1, it's going to multiply by 4. And we get this stretched out graph here, vertically stretched. So that gives us the graph of g of x equals 4 times the absolute value of 3 minus x. Solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. We have this polynomial inequality, The polynomial is x squared minus 22x plus 121. And then our inequality is less than 0. So with polynomial inequalities, we want to start off by finding the boundary points. And that means solving the equation x squared minus 22x plus 121 equals 0. So I replace that inequality with an equal sign. These boundary points, if you're thinking of this graphically, like a two-dimensional xy graph, these would be your x-intercepts of the polynomial. So let's see if we can solve this by factoring. If not, we can always rely on the quadratic formula. So I know that x times x is x squared. 121, I think that's 11 times 11. And I can make them both both minuses, because negative 11 times negative 11 will give me a positive 121, and negative 11 plus negative 11 will give me a negative 22. So I've got that factored correctly, and then I'll set each factor equal to 0 with the zero product property, and that gives me x equals 11 and x equals 11. Now, I only need, because those are repeated, I only need one of them, and I'm going to put that boundary point on the number line. And when I put it on the number line, I can also take note of that original inequality. Notice it's a less than. Less than doesn't include equal to. So this boundary point will not be included in our solution set. So we know that 11 is not part of the solution set for this inequality. And now what we need to do is test whether the interval to the left of 11, so numbers less than 11, are part of the solution set, or numbers greater than 11 are part of the solution set. So we want to pick test points in each one of those intervals. So I'm going to pick a test point, and the only rule is that it has to be in the interval. So we need to pick a number that is less than 11. So I'll pick 10. And in the other interval, I'll choose a test point that is greater than 11, so 12. And what you do is you take that test point and you substitute it into your inequality to see whether you get a positive or a negative. So let's substitute x equals 10 into our polynomial. That's 10 squared minus 22 times 10 plus 121. 10 squared is 100. 22 times 10 would be 220. 100 plus 121 would be 221. And we have 221 minus 220 would give you a positive 1. And so that means in this interval, our y values will be positive. Then I'll test x equals 12. So if I test x equals 12, I get 12 squared minus 22 times 12 plus 121. 12 squared is 144. 22 times 12 is 264. 144 plus 121 is going to give me 265 minus 264 is a positive 1. So in this interval, my y values are positive based on that test point. So when I go back to my original inequality, In order to make this inequality true, I need the y values to be less than 0. I need them to be negative in order for them to be included in the solution set. So my intervals came out positive, so they're not included in the solution set. And my boundary point is also not included in the solution set. So this inequality has no solution. If you want to think of this graphically, the graph is going to be a parabola shifted to the right 11, and it would look something like this. And so you can see down here where the y values are negative, the graph isn't present on that part of our coordinate plane. So we have no solution to this inequality. In this example, we want to use the intermediate value theorem to show that the following function has a 0 in the given interval. Approximate that 0 correct to 2 decimal places. The polynomial function that we're working with is f of x equals 6x to the 4th minus 2x squared plus 5x minus 1. And we want to approximate this 0 on the interval from 0 to 1. So I got here the definition from our book of the intermediate value theorem. It says, let f denote a continuous function. So the function we're working with is a polynomial function, and polynomial functions are continuous. It says if a is less than b, and if f of a and f of b are of opposite signs, then f has at least one 0 between a and b. So in order for us to show that the function has a 0 in this interval, we need to test the y values. F of a and f of b are y values, and we need to see that they have opposite signs. So we need to calculate f of 0, and f of 0 would be 6 times 0 to the 4th minus 2 times 0 squared plus 5 times 0 minus 1. So that works out to be -1. And we need to test f of 1. That's 6 times 1 to the 4th minus 2 times 1 squared plus 5 times 1 minus 1. That would be 6 minus 2 plus 5 minus 1. So 11 minus 3 is a +8. And we can see that the y value here is negative and the y value here is positive, so they do have opposite signs. And so using the intermediate value theorem, we've now determined that there will be a 0 between these two x values. So there is a 0 between 0 and 1. There is an x-intercept between 0 and 1. So then we want to approximate those zeros correct to 2 decimal place. Now I'm sure there are many ways you can go about approximating those zeros, but I want to continue to use the intermediate value theorem. And I'll bring my graphing calculator in. And with my graphing calculator, I'm going to type that function into the y equals menu. I've got 6x to the 4th minus 2x squared plus 5x minus 1. And I'm going to use the table feature in my calculator. So I need to set this table up so it works properly. And I've got in here table start. So I want my table to start at 0, and I'm choosing 0 because that's the interval we're working with. So we want to start at 0. And I am looking to figure out the first decimal place. So I'm going to make this change in table. So it's going to increment every 0.1. And then I also need to change this to auto instead of ask. So I'm going to go into the table now, and you can see that my x's start at 0 and then start increasing by 0.1. Now again, I want to use my intermediate value theorem. So let me get a screenshot of this table so that we can write on it. So using the intermediate value theorem, it says that if we have a change in the sign, if we have opposite signs, then we are guaranteed to have a 0 between them. So looking right here, I have a change in the y values negative to positive, so that means I've now narrowed my window down. Originally, we used the intermediate value theorem, and we said that we had a 0 in between 0 and 1. And now we've narrowed that window down, and we now know that the 0 is in between 0.2 and 0.3. So now we know one decimal place. Let me bring my calculator back, and we're now going to see if we can get a second decimal place. So what I'm going to do is now I'm starting at 0.2. I'm going to go back to my table set, and I want to start at 0.2, and I want to get even more detail, so I'm going to go to 2 decimal places. Let's take a look at the table. And let's get a screenshot of this. Okay, so I got that screenshot. And I'm using that intermediate value theorem again, looking for opposite signs. So you can see here that the sign changes from negative to positive, and we have now narrowed the window down even more. So we now know that that 0 is in between 0.21 and 0.22. Now I want to do this one more time, and the reason why I want to do it one more time is because of rounding issues. We want to have it accurate to 2 decimal places, but if we are rounding up or down, depends on what the next digit is. So we want to know if the next digit is 5 or above, or if it's below 5, so we can figure out that rounding. So let's bring our calculator back again. And I want to go into that table set, so I'm going to hit second window. And now I want my interval to start at 0.21. And I'm going to get even more granular, 0.001. So we can now figure out this third decimal place. And let's go into the table. And once again, we're looking for that change in signs. You see the negative to positive right here. Let's get a screenshot of that. So now we can see, based on the intermediate value theorem, a change in signs. And so we're narrowing down where our 0 is even more. So now we know it's in between 0.216 and 0.217. And based on that next digit, I'm now going to round up. So we're going to say that 0.22 is our 0. So because both of those digits were greater than 5, I'm rounding up to 0.22. We want to solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. The polynomial inequality that we're working with is x squared less than or equal to 8x minus 13. So the first thing that I want to do is rewrite this so that I have 0 on one side of the inequality. I'll move all those terms to the left-hand side to give x squared minus 8x plus 13 is less than or equal to 0. Having a 0 on one side of your inequality is really important to the process because it tells us what sign we're looking for, whether we're looking for positive, negative, or 0. So because this inequality has less than, that means that we're going to be looking for negative values. And because we have the equal to, we're also looking for values that equal to 0 that solve this inequality. So we'll start off by finding the boundary points. And to find the boundary points, we're going to solve the equation x squared minus 8x plus 13 equals 0. So you can think of these as boundary points or x-intercepts. So if I try to solve this quadratic equation by factoring, I think we're going to see that it doesn't factor. X times x is x squared. The only factors of 13 are 13 and 1, and those won't produce the 8 in the middle that we need, that negative 8 in the middle. So factoring is not going to work, but we could use completing the square or the quadratic formula to solve. So I'm going to use the quadratic formula. I need to know the coefficients. A is 1, B is negative 8, and C is 13. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. We'll substitute those coefficients into the quadratic formula to give negative 8 plus or minus the square root of negative 8 squared minus 4 times 1 times 13 all over 2 times 1. We'll simplify. Negative 8 is a positive 8. Negative 8 squared is 64. 4 times 13 is 52. And that's a minus 52 all over 2. 64 minus 52 would give me a 12 underneath the radical. 12 is the same thing as 4 times 3. And I can take the square root of 4. The square root of 4 is 2, and the 3 stays inside the radical. And then finally we have 4 plus or minus square root of 3 if I divide that 2 into both those terms. So I get boundary points of 4 plus square root of 3 and 4 minus square root of 3. I'm going to put those points on my graph for minus square root of 3 and 4 plus square root of 3. And because our inequality is going to include equal 0, we're going to include these boundary points. So these 2 points are solutions to that inequality. So now I need to test each one of these intervals. So I need points in each one of those intervals. Before I can choose points, it would be helpful if I knew what 4 minus square root of 3 is and 4 plus square root of 3 is. Otherwise, I'm just guessing. So let's, in the calculator, write 4 minus square root of 3. That's 2.27. And 4 plus square root of 3 is 5.7. So now I can be more careful about my test points. I need to pick something that is less than 2.27, and 0 is a good choice there. I need to pick something that's in between 2.27 and 5.7. Let's pick 4. And I need to pick something that's greater than 5.7. Let's choose 6. And we're going to substitute those test points into our polynomial or quadratic. So for x equals 0, we get 0 squared minus 8 times 0 plus 13. And that works out to be 13. So in this interval, we have positive y values. And then we're going to continue to test x equals 4, the next test point. That would be 4 squared minus 8 times 4 plus 13. So let's see, that's 16 minus 32 plus 13. That's a negative 16 plus 13. That works out to be negative 3. So in this interval, our y values are negative. And then our final test point, x equals 6, would give us 6 squared minus 8 times 6 plus 13. That would give us 36 minus 48 plus 13. And 36 minus 48, that's a negative 12 plus 13, and that's a positive 1. So in this interval, we get positive values. And now that we've filled out our interval, we can answer which intervals of numbers are going to satisfy the inequality. So you remember earlier we said because this inequality is less than or equal to 0, we want the negative and equal to 0. So we've got negative in the middle, and the boundary points are going to equal 0. So only that interval will provide solutions. We want to use the numbers in the exact form, which is this square root 4 minus square root of 3, because that would be the exact answer. And then we have 4 plus square root of 3. So our solution set for this inequality would be all numbers that are in between 4 minus square root of 3 and 4 plus square root of 3. And I use the brackets to include those boundary points. In this example, we want to form a polynomial with real coefficients having the given zeros, given degree in zeros. So in this example, we have a polynomial that has degree 4, so that means that we're going to have 4 zeros. We're given some of those zeros. We have a 3 with multiplicity 2, and so what that means is that 3 is a repeated 0. We have 2 factors of x minus 3. So when we have multiplicity, that means we're going to have repeated factors of the same 0. And then we also have a 0 of 6i. Now this one has that complex 0. And with that complex 0, and the fact that this polynomial has real coefficients, we know that the conjugate, negative 6i, is also a 0. So this gives us our 4 zeros. We have the 2 repeated 3's, we have the 6i, and using the conjugate pairs theorem, I know I also have a 0 of negative 6i. So this is going to allow me to form the polynomial using all those zeros. So our polynomial, f of x, will be some coefficient multiplied by x minus the 0. And remember, because 3 is repeated, we put 2 factors of that. Because it has multiplicity 2, we have 2 factors of that. And then we have 6i being a 0, so x minus 6i is a factor. We have negative 6i being a 0, so x minus negative 6i is a factor. So we found this polynomial that has the zeros that we're interested in. I'm just going to simplify this last one. Minus and negative is the same thing as plus. So you have 6 plus I. And we're going to simplify it by putting it in expanded form. Right now it's in factored form. I'll multiply these 2 factors together, and I'll multiply these 2 factors together. So x minus 3 times x minus 3 would be x squared minus 3x minus 3x plus 9. Putting x minus 6 times x plus 6 would give me x squared plus 6i minus 6i minus 36i squared. And that would give x squared minus 6i plus 9. And x squared, these middle two are opposites, so they zero out. And that becomes a plus 36 because I squared is negative 1. And negative 1 times a negative 36 would be a positive 36. And I'm going to multiply a little bit more. Now I can multiply these two together. And that would give, let's see, I'll write a bracket here. And I'm going to multiply the x squared times everything over here. That's x squared times x squared plus 36. Then I'll multiply the minus 6i times everything over here. Minus 6i times x squared plus 36. Then I'll multiply the 9 times everything over here. So plus 9 times x squared plus 36. A little bit more multiplying to do. I'll distribute to these parentheses. And that would give x to the 4th plus 36x squared minus 6ix squared minus, and what is 36 times 6? That's 216i Then I'll subtract. I apologize. I just noticed a mistake I made, and I'm going to correct it because I really shouldn't have any i's in here. So let me highlight the mistake I made. This is a 3x. This should also be a 3x, and when you combine them together, you get 6x. So this should be 3x and 6x. This should be an x. So let's make that correction. So when I distribute, that becomes 6x cubed minus 216x. And when I distribute, I'll have 9x squared, and 9 times 36 gives me 324. I have some like terms I can combine. I can combine these two x squareds together, and I'm also going to write this in descending order, meaning the highest degree first. So I have x to the fourth minus 6x cubed. 36 plus 9 would give me 45x squared minus 216x plus 324. So any multiple of this polynomial would give me these zeros that we listed above. It's a fourth degree polynomial with repeated zeros of 3 and zeros of 6i and negative 6i. Information is given about a polynomial function f of x, whose coefficients are real numbers. Find the remaining zeros of f. Our polynomial has a degree 6, and we were given some of the zeros. So we have 1 0 of 3. We have a 0 of 3 plus I. We have a third 0, negative 5 plus I, and a fourth 0 of 5. So the reason why I was numbering the zeros is because when we have a polynomial of degree 6, the fundamental theorem of algebra tells us that we will have 6 zeros. So we have 4 zeros here. We have 2 more to find. Now, this polynomial has complex zeros. These two have I in them. And our polynomial has real coefficients. And because of that, we can apply the conjugate pairs theorem. And the conjugate pairs theorem says that as long as we have real coefficients, then the zeros come in pairs. The complex zeros come in pairs. So this complex zero will indicate that the conjugate 3 minus I is also a zero of the polynomial, and negative 5 plus I, the conjugate of negative 5 minus I, is also a zero. So this gives us our number 5 0 and number 6 0, and we've identified the remaining zeros of this polynomial function. Use the remainder theorem to find the remainder when f of x is divided by x minus 1/5. Then use the factor theorem to determine whether x minus 1/5 is a factor of f of x. We have our polynomial f of x equals 5x to the fourth minus x cubed plus 15x minus 3. So let's start with the remainder theorem. The remainder theorem gives us a shortcut so that we don't have to go through the division process. The remainder theorem says that if we're trying to figure out the remainder when dividing by x minus 1/5, then we can take the value, we can kind of think of it as the 0. So if we were to set that factor equal to 0, we would get x equals 1/5. So in order to figure out that remainder, we're going to take 1/5 and substitute it into our function. So we're going to calculate f of 1/5. And this will give us, this calculation will give us a shortcut to finding the remainder when f of x is divided by x minus 1/5. So let's do that. Let's calculate the remainder using the remainder theorem, and we would get 5 times 1/5 to the 4th power minus 1/5 to the 3rd power plus 15 times 1/5 minus 3. So applying these exponents, that's going to give me 5 times 1 to the 4th over 5 to the 4th minus 1 cubed over 5 cubed. And then this is a plus 15 over 5 minus 3. Now 1 to the 4th and 1 to the 3rd is 1. So I have 5 times 1 over 5 to the 4th minus 1 over 5 to the 3rd. 15 over 5 is 3. And then I put the 5 over 5 to the 4th. If I'm being honest with you guys, I'm doing it this way so I can avoid figuring out what 5 to the 4th power is. I don't know that in my head. And 3 minus 3 over here is 0. 5 over 5 to the 4th. I can cancel out one of those 5s. And I get 1 over 5 cubed minus 1 over 5 cubed. That's 0. If you wanted to work it out, that's 1 over 125 minus 1 over 125, and that's 0. So we found that the remainder is equal to 0 using that remainder theorem. So we were able to find the remainder, but then we want to go a step further. And let's see if I can zoom back out here a little bit. So we found the remainder, but we also want to use the factor theorem to decide whether x minus 1/5 is a factor of that polynomial. So the factor theorem says if the remainder equals 0, then we have a factor. So combining that remainder theorem with the factor theorem, we can now say because our remainder came out to be 0, then yes, x minus 1/5 is a factor of our polynomial f of x equals 5x to the 4th minus x cubed plus 15x minus 3. So on this example, We have a polynomial function that's below. That's f of x equals -8 times x plus 1/2 squared times x plus 3 cubed. And for this polynomial, we want to list each real zero and its multiplicity, determine whether the graph crosses or touches the x-axis at each x-intercept, determine the maximum number of turning points for the graph, and determine the end behavior, that is, find the power function that the graph of f resembles for large values of absolute value of x. Okay, so conveniently, this function is written in a factored form, so identifying the real zeros, which are the same thing as x-intercepts, it's very easy to do that in factor form. So we can take each factor, set it equal to 0, and solve. So we have -1/2 being 1, 0. We'll take this other factor of x plus 3, set it equal to 0, and solve. And we have real zeros, which are x-intercepts, of -1/2 and -3. So our zeros are -1/2 and -3. We also want to identify the multiplicity of those zeros, and the multiplicity of those zeros can be found using how many times those zeros are, or those factors are repeated. So because we had a factor of x plus 1/2 and another factor of x plus 1/2, we say that -1/2 has a multiplicity of 2. And we have x plus 3 times, x plus 3 times x plus 3 times x plus 3. That zero has a multiplicity of 3. We can use this multiplicity to determine the behavior at that x-intercept. We can determine whether the graph crosses or touches the x-axis at that x-intercept. So when we have an even multiplicity, that tells me that the graph will touch the x-axis at that point. And when we have an odd multiplicity, the graph will cross at that point. Then in this next part, we want to determine the maximum number of turning points. In order to determine the maximum number of turning points, we have to know the degree of this polynomial. So the degree of the polynomial we're going to get by how many factors on the variables we have here. We have 2 factors on this one and 3 factors on this one, so we have 5 factors of x. That's going to give us a degree of 5. So then, once we know the degree, the max turning points is always going to be 1 less than that degree. So the maximum number of turning points would be 4. So then our final part here is to determine the end behavior of the graph. So to determine the end behavior of the graph, we want to pay attention to our leading coefficient here, as well as all our variable terms. So if we apply the power to the variable and then multiply, we're going to have a leading term of -8 x squared times x cubed, and that's -8x to the 5th. So our power function for this graph is going to be -8 x to the 5th. And just to give you a little bit more detail about that, what that means for n behavior, we're going to look at two components of this leading term. You can look at the degree and the leading coefficient. Now the degree is odd, and what that tells me is that the n's are going to go in opposite directions, one negative and one positive, where it might be positive on the left, negative on the right. But then when we focus in on the leading coefficient, it tells me which one. So it tells me this one right here. Meaning that on this side of our graph, where x is near negative infinity, our y will be positive. And then over here on the right side of the graph, the y will approach negative infinity. On this one, we want to determine whether the following function is a polynomial function. If the function is a polynomial, state the degree. If not, tell why. Then we want to write the polynomial in standard form, identifying the leading term and the constant term. The function we're working with is g of x equals 4 minus x to the 4th over 3. So at first glance, you might think that this is not a polynomial because of the fraction bar, but it is a polynomial because the denominator doesn't have a variable in it, and we could rewrite this, getting rid of the fraction. So I would divide 3 into each one of those. We would have 4/3 minus 1/3 x to the 4th. And then I would write this in descending order. That would be negative 1/3 x to the 4th plus 4/3. And you'll notice here, I'm going to pause for a second to make sure that we know what a polynomial function looks like. The terms of a polynomial function will follow this pattern ax to the n. And the rules are that this a needs to be a real number, and this power, n, needs to come from the non-negative integers, meaning that they need to be 0, 1, 2, 3, 4, and so on. So in order to check to see if this is a polynomial, I'm looking at these coefficients. So these numbers here, these are both real numbers. And then I'm also looking at this power, and I'm checking to see if this power is a non-negative integer, and it is. So we do have a polynomial function, and I've just written it in the standard form. The leading term would be the negative 1/3 x to the 4th, and the constant term is going to be a term with no variable. That's going to be the 4/3. And we also need to state the degree of this polynomial, and the degree is 4. That's that power on the x. If there's more than one power, you take the highest power on x. An athlete whose event is shot put releases a shot. When the shot, whose path is shown by the graph to the right, is released at an angle of 65 degrees, its height, f of x in feet, can be modeled by this equation. F of x equals negative 0.04x squared plus 2.1x plus 6.1, where x is the shot's horizontal distance in feet from the point of its release. Use this model to solve the parts and verify your answer using the graph. So we have here the graph, which is the model of the shot put's throw. So we have the shot put's horizontal distance and the shot put's height. So in part A, we want to know what is the maximum height of the shot and how far from its point of release does it occur. So we want to know that using the picture here, we can kind of estimate it, and it looks like the maximum height is going to be probably about 34 feet, and how far from its point of release it looks like to be maybe 25 feet. But we're going to be able to find the exact answers using the function that we're given here. So we have f of x equal to negative 0.04x squared plus 2.1 x plus 6.1. So because this is a quadratic function, I know that the maximum height is going to occur at the vertex. And I can use the vertex formula to find out what that horizontal distance is and also what that maximum height is. So the vertex formula will be negative b over 2a. So b is 2.1. So we'll do negative 2.1 over 2 times a, and a is negative 0.04. So we'll do 2 times negative 0.04. So that's negative 2.1 over negative 0.08. Let's grab our calculator. So using the calculator, we have negative 2.1 divided by negative 0.08. We have 26.25. So this is going to be our distance from the point of release. And then to know the height, we can substitute f, our function, represents the height. So we can substitute this 26.25 into our function to find what that maximum height is. So we want to do negative 0.04 times 26.25 squared plus 2.1 times 26.25 plus 6.1. So let's put that in the calculator. We got negative 0.04 times 26.25 squared plus 2.1 times 26.25 plus 6.1. We have 33.6625. And that's also feet. So for part A, our shot put reaches a maximum height of 33.6625 feet, 26.25 feet from the point of release. Okay, so I went and got part B. What is the shot's maximum horizontal distance to the nearest tenth of a foot, or the distance of the throw? So using our picture, you can see over here that the shot would end right here. Looks like in between 50 or 60. If we're going to estimate, it looks like to be about 55. But we want to find that exactly and not guessing from this picture. So we're going to solve it algebraically. And to solve it algebraically, the end of our throw here is going to be when it hits the ground. That's when the height is equal to 0. So we can find the maximum distance that the throw has by setting our function equal to 0. So we're going to solve f of x equal to 0. That's negative 0.00, excuse me, one too many 0 there. 0.4x squared plus 2.1x plus 6.1 equal to 0. And I am going to use the quadratic formula on this, but it can be a little bit challenging with these decimal values. Maybe I'll just leave it that way. I was thinking of getting rid of the decimals. Maybe I will get rid of them. So I'm going to multiply by 100 and also divide by a negative. If I multiply by 100, this becomes negative 4x squared plus 210x plus 610, and if I get rid of that negative in the front, it will be 4x squared plus 210x. Oh, that would be a minus 210x and minus 610 equals 0. So this just makes a little bit nicer numbers in my quadratic formula. So using the quadratic formula, a is 4, b is negative 210, and c is negative 610. Got x equals negative b, that's negative 210, plus or minus the square root of negative 210 squared, minus 4 times negative 610, all over 2 times 4. So I have 210 plus or minus the square root. I need to know what 210 squared is. That's a big number, so maybe I made a bad choice here. But that's okay. So then I need to do 4 times 4 is 16 times 610, and that gives me a plus 9,760 over 8. Got 210 plus or minus, and we need to do 44,100 plus 9,760, and that gives 53,860 over 8. And I think because these numbers are not very nice, let's go ahead and just use our calculator to simplify. So I'm going to do 210 plus the square root of 53,860 divided by 8. And so we have 55, and what did it say to round to? The nearest tenth, so let's do 55.3. And there's one more x-intercept, and it just has a minus right here. So 210 minus square root of 53,860 over 8, and that's a negative value, which doesn't make sense. So really we can throw that one away. So we have a maximum horizontal distance of 55.3 feet. All right, so we have one more part, and that question is, from what height was the shot released? So I'm going to zoom out a little bit so we can see that picture that they gave us again. And based on this picture, it looks like the original height is in between 5 and 10 feet. But we can figure out what that number is exactly by letting the horizontal distance be 0. So if we do the calculation f of 0, this is going to give us the original height. So that's a negative 0.04 times 0 squared plus 2.1 times 0 plus 6.1. And we end up getting 6.1 feet as the original height of that shot. Farmer Ed has 550 meters of fencing, and he wants to enclose a rectangular plot that borders on a river. If Farmer Ed does not fence in the side along the river, find the length and width of the plot that will maximize the area. What is the largest area that can be enclosed? So let's start by drawing our picture. We have a rectangular plot that is alongside of a river, and we're not going to put up fencing along the river. We have 550 meters of fencing, and so the fencing is going to go up along these 3 sides here. So we want to place that fencing in a way that it creates the maximum area inside. So we want to have the max area inside. Now with a rectangular plot like this, it has 2 dimensions. It has the length and the width. So we have the length and the width here. Because we're only using 3 sides, we're going to have 2 of the widths and only 1 of the lengths. And I can use that 550 meters of fencing, and if I take away the 2 widths, I have a formula to come up with the length. Now remember, our goal is to find the maximum area, so if we write out the formula for area of a rectangle, that's going to be length times width. But I'm going to get rid of the length by writing in that formula that I have, 550 minus 2w times w. If I distribute that w, I have the formula 550w minus 2w squared. And you can see that this is a quadratic equation. Negative 2w squared plus 550w. So since we're trying to find the maximum area, and this is a quadratic, I know that the maximum area is going to occur at the vertex. So I'm going to use the vertex formula, negative b over 2a, and a is negative 2 and b is 550. That's negative 550 over 2 times negative 2. So 550 times negative 550 divided by negative 4. Let's see, that works out to be Sorry, I'm having trouble doing math in my head. Works out to be 13.75. And I can substitute this into the area function to find out what that maximum area is. So that's going to be -2 times 13.75 squared plus 550 times 13.75. So let's get our calculator for that. We've got -2 times 13.75 squared plus 550 times 13.75. So we have a mistake in how I calculate it. Let me do that over again. I have this extra parenthesis here. So -2 times 13.75 squared plus 550 times 13.75. So our maximum area would be 7,184 and 375 thousandths. So 7,184,375. So this number right here represents the width because the width is the variable that's used in our equation, and this one represents the area. So we're going to have a max area of 7,184.375 meters squared when we set a width of 13.75 meters. Let's read the directions one more time. Find the length and the width. I found the width, but I haven't found the length. So let's find the length. So, and a length of, I'll do 550 minus 2 times the width. That's 13.75. So I'll bring my calculator back and do 550 minus 2 times 13.75. So 522.5 meters. So we have a maximum area of 7,184.375 with the width being 13.75 and the length being 522.5 meters. Thank you for checking out my videos. Have a great day.